I'm going to be talking to University of California at Santa Cruz chemistry professor Scott Oliver about a breakthrough his team has made. And they figured out how to make cheap, easy hydrogen. And with the emphasis these days on hydrogen as maybe it'll be 25 or 30% of primary energy by 2050, some estimates. It's a very intriguing discovery. So welcome to the interview, Scott.
Thank you. Great to be here.
Now, I was reading the story behind this, and it seems almost serendipitous, this discovery.
That's true. Yeah, it was discovered by my colleague, Bhaktan Singram. He had an undergrad that was in his classes. Isai Lopez actually discovered it in his kitchen. Yeah.
That's a great story. We'll get into the details of what it is, what the process looks like. But please tell me how an undergraduate student discovered potentially a huge innovation in making hydrogen in his kitchen. I need to know that.
Yeah, not recommended to play with chemicals at home, but you can buy gallium, on Amazon, and there's videos out there. Like, it was known you can take aluminum metal, gallium metal, mix them together, create hydrogen when you add water. The problem was most people is the ratio of those two. That's the key. You would think the more aluminum you have, and we'll get into the reaction, you would get more hydrogen. Turns out you should have less aluminum. And so you want the gallium to stay liquid. And that's what our process involves. And he discovered you dissolve the aluminum into the gallium, keep it as a liquid, and that once we started collaborating, we discovered there's nanoparticles of aluminum floating around in the gallium, and that's responsible for the reaction. And yeah, it was an accidental discovery. It was just trying to alloy them. We're told not to play with liquid hydrogen, so
don't do this at home, folks. Yeah. Okay, so if I understand this correctly, aluminum reacts with gallium and creates hydrogen, but there's a problem with it also creates a coating at the same time, which kind of inhibits the process, which is why it hasn't been economic. So it turns out that, this was discovered as far back, at least in the 1970s, according to the story I was reading. So in all that time, nobody thought to just play around with the proportions of aluminum to gallium and see if that made any difference.
Yes, it's really as simple as that. It's the aluminum is what's causing the reaction. So the more aluminum, I guess people, they just the patent that's out there from years ago has more aluminum than gallium. And Isai, was playing around with the ratios.
So, okay, and I think it's important to note that this requires no energy.
No, yeah, that's a key point. No energy, no CO2 whatsoever. You just take your aluminum metal, it splits the oxygen and hydrogen in water. You get aluminum oxide, and hydrogen gas comes off. Yeah, the only thing that's left after is aluminum oxide, which is also useful, and the liquid gallium remains.
Are there plans to patent this innovation and then to commercialize it in a startup and try to scale it up?
Yep, that's exactly. We have a patent application that just got published about a month ago, and so people can view that online. And yeah, it's exactly where we're headed: startup and scale up.
Now, I don't do a lot of these interviews with scientists who have made lab breakthroughs because there are so many of them, and then very few of them actually make it to commercial application. But this one just seemed the essence of simplicity and a candidate ripe for scaling up. And so how long do you think it's first of all, what's the potential here? We make green hydrogen with electrolyzers, and then, it's going to be years before that's economic. Can you do it economically at scale, and how quickly can you do it?
Yeah, that's another thing. The photovoltaic solar cells, everybody thinks you got to buy the material, you have to make the solar cells. That's energy intensive. We just take the liquid gallium and it goes. You need a source of aluminum. So, when you throw out your aluminum can, aluminum wrapper, that represents energy. And that's what we're harnessing when we make the hydrogen. And you know, the scale up, I don't see a limit to it. We were limited by the size of our reactor. That was all. Yeah.
Okay, so it's important, I think, for our viewers to understand the gallium gets recycled completely.
That
When
is a
there's
key thing. You got to get it all. Yep.
So it's the chemical reaction between the gallium and the aluminum that splits the molecules in the water. But you don't have to add any energy. Nothing gets lost from the aluminum or the gallium. I mean, this almost sounds like a perpetual motion machine.
Yeah, I see comments out there, you know, it sounds too good to be true. It kind of, you know, no energy input, no catalyst needed, no potential. You don't need electricity. You know, if you're off the grid somewhere and you have these, you could make hydrogen. And the gallium, it does need a tiny bit of heat. It melts just above room temperature. But the reaction, once it goes, it gives off heat. So just keep going. The gallium serves to dissolve the aluminum, keep it separated as nanoparticles, and protects it from forming an oxide shell. Like, you know, aluminum foil, Reynolds wrap, has an oxygen surface, you know, aluminum oxide surface that prevents it from reacting with water. So the gallium helps to remove that.
What has been the reaction of other scientists? I mean, you know, scientists generally, you know, can they replicate the work that's been done in other labs to verify it? Has anybody else, you know, done that?
Not to my knowledge. We've had a lot of correspondence. You know, we did the press release back when we released the paper, and we got some contacts from that. And then last week it got picked up by Science Alert, which then led to Newsweek, and now the Chemical Engineering Society or institution. So it seems to be gaining more interest just in the last week. It's just that most people don't know about it, I think.
Okay, well, this is fascinating, and we're going to stay in touch with you, Scott, because I want to see if this actually, you know, if it can be scaled up, if it can become commercial, because the potential just seems to, I mean, be unlimited at a time when the world needs it. So thank you very much for this. Really appreciate it.
Yeah, thank you very much.